What is it that we're going to be doing today? We have our review final sheet of problems that we've actually used to prepare for our part-time or midterm exams. And we'll take a look at some of those. So I'm talking about this list of problems you may remember. And so even though it says spring 2019, it's the same as spring 2020, don't mind that. And it's sort of in chronological order, in the order in which we cover the topics, starting from the very section, the very first section we did this semester, 7.3. And so we're gonna go through those problems. But before we do that, I wanted to give you an overall sense of all the material that we've covered throughout the semester. So let me show you. I wrote it down in a page. I organized it more or less into three chunks, three parts, three big parts. So we have this one over here first. So we did right here. So we started with chapter 7. And we looked at inverse trigonometric functions. So we learned about arcsine, arctangent, fundamentally, then arccosine, and less so arcsecant, arccosecant, and arccotangent, or inverse tangent, inverse secant, etc. We learned about logarithms. So not only ln, but logarithms to other bases like log 10, log 2, log 5, exponential functions, not only e to the x, but any other base number like 2 to the x, 5 to the x, so on. We did L'Hopital's rule on the more elaborate case of when we have two exponents and our indeterminate looks like 0 to the 0 power or 1 to the infinity or infinity to the 0. And we did growth of functions, like which functions are grow faster than others. You may remember that one as well. So that was essentially chapter 7. It wasn't the entire chapter 7. The first two sections were done on 158. So this was only a few sections in chapter 7. Then we move on to chapter 8 about integration and or more general techniques of integration. We learned about integration by parts. We learn about how to do trigonometric integrals, products of sines and cosines, fundamentally, and products of secant and tangent. Then we learn trigonometric substitutions, what three subs to use to deal with fundamentally x squared plus a constant square, x squared minus a constant square, or a constant square minus x squared. We learn partial fractions to deal with integrals of rational functions. And we learn about improper integrals. These are integrals where the integrand is not continuous. It's undefined at some point in the endpoints or in the middle of the interval, or when we integrate all the way to infinity or from negative infinity to infinity. So that was the last section in chapter 8, which is or was also a segue. It's the only thing that is somewhat related to the next chapter, which was sequences and series. So I have it right here on the right. So the sequences and series chapter started with, we talked about sequences, which was easy. It was a little bit like doing regular limits. We talked about partial sums, which is the way in which we define series and when a series was convergent or divergent. And then we presented some nice examples of telescopic series. Those were those that we could calculate the partial sums and somehow everything canceled and we could get a nice, neat expression for the partial sum and then evaluate the limit when n goes to infinity. Another example of that type of telescopic one was a geometric series, which were also important as a base case for our later tests to know whether a series was convergent or divergent. And we did the integral test, and the integral test is the one that is related to improper integrals over here, right? it tells you that a series is convergent or divergent, whether the corresponding integral is convergent or divergent, right? So to know one of these, you do an integral, an improper integral, and then once you do it, you know if it's convergent or divergent. And we learned the comparison and the limit comparison tests, which a great tool to enlarge our notion of which series were convergent or divergent based on the ones that we already knew. An example of these were the an example of the integral test. So maybe I should add it over here. So this also includes the P series. So the P series, we did them with the integral test. And then we could use those for all kinds of comparisons. We learn about the alternating series test for those that are alternate positive and negative ones. The absolute convergence test, when we make the absolute value of the terms and we check that one, and if that one converges, then the original one converges as well. And that led to this concept of absolute convergent series or conditionally convergent series. So absolute convergence series were the ones where with the absolute value they will be convergent, and in that way without it they're also convergent. And conditionally convergent, those are when the absolute value ones are divergent, but the regular ones are convergent. All right? So that's a summary of chapter 10. And we went on to chapter 11, which if I had to title it, it would be power series. So now we had a variable inside the series, a variable x, and we started first talking about Taylor polynomials, which were not series, but rather just our best approximation using first lines, then parabolas, then cubic equations, and so forth. Then we went into power series. We learned how to figure out the radius and the interval of convergence. Right about here is where we started having our Zoom sessions. So I think Taylor polynomials was the last topic we covered in the classroom. This is more or less where we started the Zoom sessions. Then we learn about known power series, starting with the geometric one. We could do all kinds of things, add them, substitute other values, take derivatives, integrate, and that way we could get other power series, like the one for arctangent, or the one for 1/1 plus x squared, and things like that. Then we learn about Taylor series, which is great. He at least gives us a procedure to get the power series of an arbitrary function, as long as we're willing to do the work of taking all the derivatives that are needed, or figuring out a pattern. And we did that. That way we could get sine and cosine and e to the x and others that are important and very relevant. Okay, and so that's the end of chapter 11. Then we did chapter 12, parametric equations. So we learned about how to do parametric equations. We said that this is the difference between having just a picture of something or having something that moves around. We learned about how to get tangent lines of parametric equations. That was an easy formula to discover. Then we learned a new system of equations. Instead of using rectangular coordinates, we use polar equations. We use those to figure out the slope of polar, how do we get the slope of the tangent line of a polar graph? We figured out the formula for that. We also figured out how to get areas inside polar curves, and also the length of polar equations. All of those formulas we discovered for polar equations, and we learned many of these involve doing integrals, and so that again goes back to all of these chapter 8, right, about integration. And then the last two chapters, the one we just covered in our previous exam. So we learned about vectors, both in the plane and in the space. We learn about how to do spheres in three-dimensional space. We learn about the dot product and how you can use it to get the angle between vectors and projections. We learn about the cross product and how you can get it, use it to find two vectors, a vector that is orthogonal, and that means perpendicular to two others, and how it can also be used to figure out the areas of triangles or parallelograms in three-dimensional space. Then we move to vector equations, a little bit in anticipation of multivariable calculus. we learn how to figure out the tangent vector to a vector equation, the unit tangent vector just by dividing by its magnitude, how we can use these vector equations to describe motion in space, and how the derivative means the velocity and the second derivative means the acceleration of that object or particle that is moving in three-dimensional space. And as our last topic, we figured out the arc length of a curve described by one of these vector equations. Okay, so that is it in a nutshell. I mean, of course, I was may have skipped over a little subtopic inside all of these that we talked about. Okay, so what is going to be our plan? So here's our plan for these few days. What I want us to do is we're going to take a look at, so today and tomorrow, we'll take a look. So today we'll do chapter 7 and most of chapter 8. Maybe we won't finish with chapter 8. We'll continue with chapter 8 tomorrow and chapter 10. And then Wednesday we'll do these two, 11 and 12. And we'll leave the last day to do 13 and 14. All right, so that's my plan. And as also, if you have questions or specific problems that you would like to know about, please do not hesitate to ask. Turn on your microphone and tell me about it. Or it doesn't need to be from our sample set of problems. If you have a problem from the book, from the homework, from a previous exam that you would like to know, please let me know. This is the week to do so, right? Last chance. Okay. So we'll start over here on chapter 7, and I'll take a look at some of the problems from our sample sheet of problems. Leave this here, and I need more paper apparently. This. Okay, so let me move to our sheet of problems. That's a review sheet, okay? And as you can tell, we start with some derivatives, right? And to do these derivatives, you of course need to know some basic derivative formulas that we discovered in that section, all right? So let's go through the ones that you're gonna need here. So what is it that you need? Well, you need to know what is the derivative of an exponential function, what is the derivative of a logarithmic function, and what is the derivative of an inverse trigonometric function, right? And then once you know that, you can do all of these problems that you see here. This problem 1 to begin with is what I'm talking about. So to do any of these, you can, so this box over here, you will need to know the formulas that I was telling you about, all right? So let's review very quickly. Let's take a look at the formulas that you need to know. So to begin with, let's start with the derivative of an exponential function. So what is the derivative of b to the x? Right? And you need to remember that they are like exponential functions. So the derivative of b to the x is almost b to the x, except you need to multiply by ln b, right? And this assume here that b is a positive real number. All right, so that's one of them. Then we also have this one, the derivative of the logarithm base b of x. And you again need to remember that this is a little bit like ln x, and the derivative of ln x is 1 over x. So this is just 1 over x, right, like this, but times a constant. So it's 1 over x times a constant, and the constant happens to be 1 over ln b, right? So these are the two main ones you need to know to take derivatives or integrals, for that matter, of the logarithm and the exponential function. Okay, so as a corollary of this one, tells you that the integral of b to the x is b to the x over ln b. Right here, you divide. See, to take the derivative, you multiply by ln b. To take the integral, you divide by ln b. Right? So these two go together. Here, well, I mean, you don't, the integral of 1 over x, you would use ln. You would never write it in terms of another logarithm. So there's not an equivalence here. And then we have the inverse trig functions, right? So which ones are those that you need to know? You need to know the ones that don't have co, right? So the derivative of inverse sine, also called arc sine, is 1 over the square root of 1 minus x squared. This one, by the way, is also useful for when you do trigonometric substitutions. So you have to know this. The one for arc tangent or inverse tangent is 1 over 1 plus x squared. And the one for arc secant or inverse secant is absolute value of x squared minus 1. All right? And then once you know these three, the ones that are co are the same but with a minus sign, right? So the derivative of cosine inverse is just minus 1 over 1 minus x squared. The derivative of inverse cotangent is minus 1 over 1 plus x squared. And the derivative of inverse cosecant is negative 1 over absolute value of x squared minus 1. Right? You can also write them as arc cosine, arc cotangent, and arc cosecant. Okay? So that's it. These are the tools you need. So we can now go back to the problem. So which one of these would you think we should do? Let's take, let's pick a few of these. Some of these, you can also use the properties of logarithms to make your life easier, right? For example, in B, you could do the formula just right away, and it would involve the derivative of log 3, and then chain rule, right? So times, eventually you're going to multiply by the derivative of the inner function, and that involves using the quotient rule. That's a lot of work. So it's probably better to first simplify using properties of logarithms. Okay, so let me do that one as an example. So 1b, that's the derivative of the logarithm base 3 of x squared over x plus 1. Take a look at that one. So like I said, I mean, there's two ways of doing this, and the better way is to first use the properties of the logarithms here. So before taking the derivative, we could simplify this as logarithm of x squared minus logarithm base 3 of x plus 1. And you can simplify this even further, because remember, this exponent can come out of the logarithm, right? So this is 2 logarithm base 3 of x minus logarithm base 3 of x plus 1. Now we can take the derivatives, and it will be easy. 2 is just a constant, and the derivative of log base 3 of x is 1 over ln 3 times 1 over x minus the derivative of log base 3 of x plus 1. That's 1 over ln 3 times 1 over x plus 1 times the derivative of the inner function, which is 1. And that's it, right? We are done, right? So that was easy. So notice I use this rule over here. We use this rule, right? The derivative of log base 3 is 1 over ln 3 times 1 over x. Okay? All right. Any other that you would like refer from this one? Let's pick another one. How about this one, F? that involves arc cosine and also 5 to the x, right? We'll at least get a chance to do both. So what is the derivative with respect to x of arc cosine 5 to the x? So we first do the derivative of arc cosine, and you may remember I have it right here. This is the formula. So that's what we do. It's a negative 1 over 1 minus whatever is inside here square. So it's 5 to the x squared. Chain rule times the derivative of 5 to the x. I'll indicate it, and I'll do it on the next step. This is negative 1 minus 5 to the 2x times. And what's the derivative of 5 to the x? Well, it's ln 5 times 5 to the x. And that's it. We are done with that. Right? Questions so far with a 1F? Or problem 1 in general? Good. If there aren't, let's take a look at this item number 2. So now these are limits, and these are limits that, I mean, derivatives that involve exponents, right? And there's two ways of doing this. One of them is the one we call logarithmic differentiation, and the other is to simply write down what it means to do a to the b, right? So I'm going to pick one of these to do, probably b. So this would be 2b, and it's the derivative of sine x to the power x. All right, and let me explain what you need to do this. There's two ways you can do it. One of them is you can think of, you can use this notion of how to do a number raised to another. So a to the b is e to the b ln a. So if you do that, then all you need to do is do the derivative of e to the x ln of sine x. And you can do that derivative just the way you usually do the derivatives. Is the derivative of e to the something, that's e to the something, times the derivative of this. And you would do that by using now the product rule. So it's e to the x ln of sine x times the derivative of x is 1 times ln of sine x plus x times the derivative of ln of sine x. The derivative of ln is 1 over times the derivative of sine, which is cosine. And I don't need this ddx. I had already taken the derivative. My bad. And that's it. I mean, you could simplify this a little bit, but this is the answer, right? So that's one way. Now the other way is essentially the same, but it's probably a bit more, a bit neater, right? The other way is to give this expression a name. So call this y. And then do the derivative of, I mean, the logarithm of that. Why? Because the logarithm brings the exponents down, and that's what our problem is right here, that we have a variable on top and a variable in the bottom as well. So take the logarithm. And like I said, the logarithm brings the exponent and down and out of the logarithm. So you get this. And now what you can do is you can simply take the derivative on both sides. So what is the derivative of ln of y? Well, it's 1 over y times the derivative of the inner function times y prime. And what's the derivative on the right-hand side? Well, you use product rule. It's the derivative of x, which is 1 times ln of sine x plus x times the derivative of ln of sine x, which is 1 over sine x, times the derivative of sine x, which is cosine x. So this is ln sine x plus x cosine x over sine x, right? And then to finish the problem, you simply solve for y prime. So to solve for y prime, you multiply by y. I'm going to write this as cotangent, looks cleaner. And then you just remember what y stands for. Y is sine x to the x. So this is sine x to the power x times ln sine x plus x cotangent x. Right? Is that clear? So that's how you do these derivatives. All of these can be done in the same way. So all the ones that you see here in these can be done the same way, right? And either way, there's no wrong way to do them there, okay? You can either, you get to do it whichever of the two ways. All right, moving along, let's now look at these integrals. So these integrals are supposed to be done by knowing the derivative formulas we learned before, together with maybe an appropriate u substitution, right? If you know an appropriate u substitution, then you can simplify them and make them better, right? I mean, you can tell, for instance, if we take a look at the first, so this one over here, what do? Well, we make u the exponent, right? You make u x cubed minus 1, then the derivative would be 3x squared, and there's the x squared. So it will look like an integral of 5 to the u, which you can, you know how to do, right? It's one of the formulas we learned before. Here, what would be the appropriate substitution to try for part B? Which substitution should be the one?
Would it be log 2x?
Yes, very good. Yeah, because the derivative of log base 2 of x is essentially like 1 over x, right? There's also the ln2, but that's a constant that we can control. Maybe we'll do that in just a moment. For this one here, you want to, this one is tricky, but here you should use as your u x squared, right? Because the derivative of x squared is 2x, and there's the x. And then after that, it's going to look like 1 over 1 minus u squared. Similar to this one, here you want to make u, and on part D, you want to make u cosine, because then the derivative of cosine is negative sine, which somehow appears right here on the top. Okay, so let's do selected few of these. Let's take a look at 3b. And maybe 3c as well. Okay, but let's start with 3b. So 3b is the logarithm base 2 of x over x. And let me write the other one before I forget as well. Or maybe 3, yeah, either one, I guess. Yeah, 3c. Okay, let's take a look at these. Okay, so yeah, like you said on this one, let's use as our u logarithm base 2 of x, which means du is 1 over ln2 times 1 over x dx. And you can tell that we have the 1 over x and the dx right here, right? So the only thing we don't have is the ln2. So if you solve for 1 over x dx, it will be du, let me write it here, du times ln2 is 1 over x dx. So that's what we do here. This will become u, if that's the logarithm. And then the dx over x is du times ln2. Now ln2 is just a constant. We can take it out of the integral. And now all we need to do is integrate u. And that's u squared over 2, right? So this is ln2 times u squared over 2 plus c, and u is logarithm base 2 of x, so that's ln2 over 2 times logarithm base 2 of x squared. And that's it. We are done, right? Leave it there a little bit. And well, we'll start thinking about this next one. So similar to this one, right? We said that this one is tricky because if you pick ux to the fourth, it's not good, or 1 minus x to the fourth, because the derivative would be x cubed. And there's no x cubed over here. So that suggests that maybe the way to go is making ux squared. That way du is 2x dx. And you can tell the x dx is right here, right? So we set x dx to be du over 2, put it in here. So this is the integral of du over 2 square root of 1 minus u squared, right? Because it's x to the fourth, and x to the fourth is x squared squared. So take the 2 out, so that's a 1/2. And now we got a formula we know, right? This one looks like the derivative of arc sine. So therefore, the integral of this becomes arc sine or inverse sine. And a usx squared, so this is 1/2 arc sine of x squared plus c. All right? Is that clear? Questions? Any other one that you would like to see from here? Or are we good? They're all similar, right? I mean, it's the important thing to note is what would be the appropriate substitution, and which one does it look like? Which one does it more closely resembles, right? Okay. Let's take a look now at these next ones. So these limits are all the types of limits that we studied with L'Hopital's rule, right? So they are all going to be limits that you cannot do by simply plugging in the numbers. See this first one over here, a. If you take a look, when x goes to infinity, this number would be infinity. Maybe, let's see if I can do it. Try my best. So when I try it, well, I'm gonna get infinity, right? Because x goes to infinity, and then to the power 1 over infinity. So that's to the power 0. Infinity to the 0, right? And that's one of the indeterminates, right? For the next one that you see after that, for part B, this time when x goes to infinity, the exponent goes to 1. So now we have 1, but the exponent goes to infinity, so it's 1 to the power infinity, right? So again, and another indeterminate. The next one, part C, the exponent, clearly the base goes to infinity, so that's infinity. And 1 over infinity goes to 0. So it's again another one that looks like infinity to the 0. And the last one right there, root of x goes to 0. So that's a 0. But ln x, when x goes to 0, ln x approaches negative infinity. And 1 divided by negative infinity becomes 0. So this is now an indeterminate of the form 0 to the 0. And these are the 3 examples of these indeterminates: infinity to the 0, 0 to the 0, or 1 to the infinity. These are the three kinds. So to do them, you need to apply, you need to call that limit L, apply the logarithm, and then use L'Hopital's rule. All right, so let's take a look at maybe we could do 2 of these. maybe let's do part B and D, B and D. So this is 4B. We want to do the limit when x goes to infinity of 1 minus 1 over x to the power 3x. All right, and we already said that this looks like 1 to the infinity. And the limit is not going to be 1, okay? Don't make that mistake. The thinking that 1 to the anything is 1. Well, not necessarily, because it's not really the number 1. It's a number that is getting close to 1. All right? So let's go to the page and see how we do it. So there's the problem. And here's how we proceed. We call that y. So we call this expression y. And L is, so L is traditionally the letter we use, is really ln of y. So ln of this. You can bypass the y if you want. You just do ln of this part over here, right? And the idea is to do the limit of the L, because the limit of the L will be easy, okay? So we do the limit of the L when L goes to infinity. So the limit when x goes to infinity of L. That will be the limit when x goes to infinity. And the nice property of the logarithms is, again, that the 3x can come out and is not an exponent anymore and comes out of the logarithm. So this is 3x ln of 1 minus 1 over x, right? And then you analyze this one. See, now this is infinity. 3x goes to infinity. And ln 1 goes to 0. So it's infinity times 0. And that's another indeterminate. And the way to make it so that we can apply L'Hopital's rule is to move one of the two to the denominator, so that it becomes 0 over 0 or infinity over infinity. And you always move the one that is easier. In this case, don't mess up with the ln, right? So we change this so that is, we leave 3 and ln of 1 minus 1 over x on the top, and we move the x to the bottom as 1 over x. And now it looks like ln of 1, which goes to 0, and 1 over infinity, which goes to 0. 0 over 0. Perfect. Now we can apply L'Hopital's rule. So for L'Hopital's rule, we need to do the derivative of the top divided by the derivative of the bottom. Let's do it. 3 is just a constant. The derivative of ln of something is 1 over that something. And then is the derivative of 1 minus 1 over x. The derivative of 1 is 0. And the derivative of negative 1 over x is 1 over x squared. Over the derivative of 1 over x, that's negative 1 over x squared. And this cancels with this. That's nice. And so I have a minus sign. So this is minus. Let me put the limit first. There's the limit when x goes to infinity minus 3 over 1 minus 1 over x. And now when x goes to infinity, this guy goes to 0. So the answer is negative 3. All right? Now careful. Remember, this is not the answer to the problem. This is the answer to the middleman, to the auxiliary guy, right? So this is the answer to L. L is negative 3. But to get the limit we want, we really want to do, and by the way, L was already including the limit. I'm not writing this correctly. L is supposed to already be the limit when x goes to infinity. That's the way we usually did it, like this. So, so then the answer to the original limit is always e to the L. Is e to the L. In this case, it would be e to the negative 3. All right? And remember, these limits do appear later on when we do the ratio test for series. We often get limits like this. So this is something that comes back later, right? It's a topic that reoccurs when we get to the series part. It's possible that you need to do a limit like this. We had one like that in our exam, if you remember that. Okay, so let's, there was another one that I wanted to do from here. Let me go back. So let's do D. So D, 4D. So that one is the limit when x approaches 0 from the right of root x to the power 1 over ln x. Okay, let's go. So this one is 0 to 1 over ln x. This approaches negative infinity. So 0 to the 0, I'm sorry. And so, as before, L will be the ln of that limit, which is 0, my bad. Which, like we said, means this exponent can come out. So it's going to be 1 over ln x times ln of root x. Oh, I remember this one. This one did not even require that much work because you can use the properties of the logarithms, right? Ln of root x is the same as ln of x to the 1/2, which is the same as 1/2 ln x. So if you use that in here, you don't even need to apply L'Hopital's rule for this one. This becomes 1 over half ln x. And the ln x's go away. So the answer is just 1/2. And that's it. So if the L is 1/2, then the answer to the limit is e to the 1/2. Good. So just to finish with chapter 7, we also had this notion of growth of functions, and we learned a bunch of things. Like we learned which functions grow faster than others, right? We had a little table in the book. Let me see if I can find it. So it would be a great summary. But in particular, this first problem over here, for instance, is essentially trivial, right? So this one over here, not a problem, right? We already know that any exponential function beats any polynomial, right? So right now this is going to be like this. So greater this way, right? So 2 to the x beats x cubed. So the f beats the g. And this one on the other side, part B, it's a little bit tricky because you need to, again, be careful here. This exponent 3, that exponent 3 on the top, this exponent 3 on the top, you can take out, right? So this is that f1 is actually the same as 3 ln x. So that's the same as 3 ln x. And that one is ln of x squared. So which one wins? If you change the ln x to a variable, it's like comparing y squared with 3y. And the higher exponent wins, right? So in this case, it's also like this, less than this one over here, all right? But the important thing to remember from this, let me show it to you, is show you the page in just a moment, is we're talking about page 497. I'll show it to you in just a moment. So this little box is the one you need to remember, right? So The logarithms always lose against any polynomial. Doesn't matter the power. Doesn't matter what P and Q are. This x to the P beats L and Q. Now, if you multiply x to the P by a logarithm, then that one is going to beat this one. But it's going to lose against any higher power. So if you use, you know, x to the 3.1, is going to beat x to the 3 times logarithm to the 100th power. It doesn't matter the 100th power for the logarithm. If this 3.1 beats 3, then this one, x to the p plus s, will be bigger. And then polynomials are always smaller than any exponential function. So if you pick any number greater than 1, that b to the x will beat this one. And in the same way, this b to the x always is beaten by the double exponential function x to the x. All right, so these are important to know. Later on in the book, when we learn about factorials, we have a different one similar to this one, where the factorial is somewhere in between. Okay, so that one is also important to know. Okay, all right, so coming back to our list of problems. So that was chapter 7, and it has a bunch of things that are relevant later on. So maybe the problem that you get on the final is not exactly one of those, but you need to use these techniques to do a problem that is more complicated, right? Okay, so then we have now chapter 8. So in chapter 8, we're gonna go over the different techniques of integration. The first kind is integration by parts, right? So for integration by parts, you want to remember the integration by parts formula, which is u dv is uv minus the integral of d du. If you remember it, this is like the product rule reverse engineer, right? So let me do, what would be a good one to do here? Maybe, let's pick one that has arc sine, or so let's do part B. 6b is arc sine, and let's do E, and it looks complicated as well. So 6e, which is e to the negative x cosine 3x. Okay, so go to page. So how do we do integration by parts? Is particularly well suited for the integrals of inverse trig functions. So if you want to do ln, arcsine, arctangent, they can all be done the same way we're going to do arcsine right now. Okay, we get a bit more paper. So how do we do arcsine? Well, there's not much there, right? We only have arcsine. So because we only have arcsine, we need to pick that as our u. So u will be arcsine, and which means that dv will be dx. So that means that v is going to be x, and du will be, well, the derivative of arcsine. And this is not what I was telling you, right? This problem requires you to know the derivative of arcsine. So even though it's not about chapter 7, it's testing material from chapter 7, right? So what is the derivative of arcsine? Well, it's the square root of 1 over 1 minus x squared. So for this one, you do u times v. That's x arcsine x minus the integral of v du. And that one is x dx divided by the square root of 1 minus x squared. And now the good thing is that this one now you can do by a u substitution, right? You can make this 1 minus x squared your u. I'm going to call it w because I already use u and d over here. Right? You don't want to use the same letters because then you can get in trouble, get confused yourself. So I'm going to call it w, 1 minus x squared. That way dw is negative 2x dx. In other words, x dx is dw over negative 2. And then I'll put it in here. So that's x arcsine x minus the integral of dw over -2 times the square root of w, right? So this is x arc sine x plus minus times minus, the 2 I can take out, and this is now w to the -1/2 dw. And now this is something we can do, right? This is just add 1 to the exponent. So it's -1/2 plus 1 is 1/2, and divide by 1/2. This goes away. And then we remember that the w is 1 minus x squared. So the final answer is square root of 1 minus x squared. Right? Is that clear? So that's how you use it for the integrals of inverse functions. You know, it works for ln, it works for arcsine, arctangent, and arcsecant. Good. Now for the other one that I wanted to do, and the other one is a bit more complicated. It requires you to, and that's why I wanted to do it, requires us to do the integration by parts twice. It's one of those in which what you get, then you need to solve for it. So if you do this one, so generally you want to use as the u the function that becomes simpler. And the problem here is that both cosine and sine do not really change when you take the derivatives, right? E to the x remains like e to the x, or e to the -x. I mean, a minus sign will happen there. And cosine will go to sine, and then when you do it again, it will go back to cosine. So that's the idea, is to do it twice and get the expression that you want back again. So here's how we can do it. We pick u either way. Both ways work here. You can pick u e to the -x, or you can pick u cosine 3x. It's really up to you. Both of them will work. The only thing you need to be careful is that you keep the same form when you reapply it, because if you change midway, you're going to come back to the one you started with. It's going to be like running in circles and not doing any work at all. So I'm gonna pick I don't really care, e to the -x, and then dv is cosine 3x. So then my du will be negative e to the -x dx, and my v will be the antiderivative of cosine 3x. So that's going to be sine 3x, but then to kill the 3 times 1/3, right? That way the 3 is eliminated and I get what I need here. Good. So we use this to put it in here. So this is uv minus v du. So u times v is 1/3 e to the -x sine 3x minus v du. Minus, there's another minus here. So it's going to be plus, and then it's 1/3 sine 3x e to the -x dx. Right? Okay, and this is where you need now to reapply it to this one. So I'm just gonna copy this one without the 1/3. So 1/3 you can take out, and I don't wanna carry it around. So then my new one is e to the -x. I'm putting the e to the -x first, sine 3x. Just like I told you, you get one that is essentially the same. So for this one, we want to again use the same form. So don't change here midway. Don't go u equals sine 3x, because then you're going to come back and it's not going to be useful. You're going to get 0 equals 0. Everything is going to cancel. You don't want that. You want to keep it in the same way. So we'll make u e to the -x dv will be sine 3x. And du is negative e to the -x. And v is the antiderivative of sine, which is negative cosine. But then to kill the 3, I need a 1/3 again. So it will be negative 1/3 times this one, right? Then we go u times v. This will be negative 1/3 e to the negative x cosine 3x minus the integral of v du. Minus the integral of v du, these two. And notice I have a minus and a minus, so those are going to cancel. So it's e to the negative x cosine 3x. All right. And you'll notice how we got the same one we started with, right? So now it's just a matter of putting it all together. So now let's put it all together. So we need to substitute this answer in here, but without the 1/3. So maybe let me put the 1/3 out. Put the 1/3 outside. So we're gonna substitute it for all of these, all right? So I'm just gonna copy here. So this is e to the negative x cosine 3x dx. Let me see if I can move a little further back so you can see. Yes, that's gonna work. So that one is this one, and now it's 1/3 e to the negative x sine 3x plus 1/3, and now this is the one we calculated, this green one. It's gonna fit in here. It's negative 1/3 e to the negative x cosine 3x minus 1/3. I'm taking this 1/3 out. E to the negative x cosine 3x dx. I'm missing the dx here. Good. And now notice we already have everything we need. This is the expression we want, and it appears on both sides. So you just need to solve for it. All right. So that's the next of what I'm going to be doing here. We can go back closer. Okay. And I just need to expand all of these. So this is the integral we want. And I'm just copying the line above. 1/3 times negative 1/3, that's negative 1/9. 1/3 times negative 1/3, that's negative 1/9. Right? Then you add this term to both sides of the equation so that it appears now on that side. So it's e to the negative x cosine 3x dx plus 1/9 e to the negative x cosine 3x dx. So the same integral, that's the important thing. And on the right hand side, that's just 1/3 e to the negative x sine 3x minus 1/9 cosine 3x. Good. Then you combine these two, so a whole plus 1/9, that would be 10/9. And here, if you want, you can factor the 1/9 and the e to the negative x. So this will be 3 sine 3x minus cosine 3x. And finally, you multiply by 9/10. 9/10 of 1/9 of e to the negative x of 3 sine 3x minus cosine 3x. And then we could put the c, right? That's the other important thing to note. Don't forget the plus c. I always see points taken off because people forgot the constant, right? So we can even cancel that 9 if you want to or not. So the answer is 1/10 e to the negative x. Write it like this. 1/10 e to the negative x times 3 sine 3x minus cosine 3x. Let's see. All right. Good. We barely have a little bit of almost no time left. So before I log off, let's check it. So let's take the derivative of this. So we never do this, and it's something you can do specifically if you're gonna have a lot of time for your exam, or you may as well check your answers, right? So Make sure that they're all right. You're gonna get a good score, do well in the class. So here, for the check, I would need to take the derivative of this. So what's the derivative of this, right? Let's see if we got it right. 1/10 is just a constant. The derivative of e to the negative x is negative e to the negative x times the thing inside plus e to the negative x times the derivative of the thing inside. So that's a 3. The derivative of sine is cosine. 3x times another 3 by the chain rule, and then minus the derivative of cosine, which is sine, so it becomes plus sine 3x, and then another 3 because of the chain rule, right? So now let's see if we can, oops, not showing you the whole page. Let's see if we can simplify this. Let's see, so there's a 1/10, and we can factor an e to the negative x. And then this will be negative 3 sine 3x, then plus cosine 3x. Then over here is plus 9 cosine 3x. And then over here is plus 3 sine 3x. And we put it all together. And you can tell how this term cancels with this one. This is 9 plus 1 is 10. And that 10 cancels this 10 over here. And we get e to the negative x cosine 3x. Perfect, right? Just like we wanted. We did it correctly. All right? Okay, so are there any questions before we log off? We'll continue tomorrow talking about, we did the entirety of chapter 7, and we did the first section of chapter 8, integration by parts. So tomorrow we'll finish with all the integration, and we start a little bit of sequences and series. That's my plan, all right? If you have specific questions, now is the time. So start studying for your final exam. Start reviewing, checking the questions you may have had from homework, from older exams, whatever you have from the review sheet, and bring them tomorrow on the few days after. Okay, it's a final push, right? Make sure you do it. You go strong for those. This is the final push. I'm hoping you do well in the final exam, and then you pass the class and enjoy the summer. All right. Any questions?
Can you go to the problem set 3?
7.3.
Yeah. For F, what would you do the U sub for?
For F in 3, the integral?
Yeah. Yeah.
I would use 3 to the x. So the integral, the derivative of 3 to the x is 3 to the x times ln 3, right?
Mm-hmm.
And that should do it. So let me write it over here relatively quickly. So I won't do the entire problem, but I'll just start you off. So if you do u equals 3 to the x, then du is the derivative of 3 to the x, which is 3 to the x ln 3. And then you can rewrite this, right? 3 to the x dx will be du over ln 3. And then this will be 1 minus, how do you write 9 to the x? Well, 9 to the x is like 3 to the x squared, right? So that's u squared. And now this should look like something you can integrate, right?
Okay. How come u squared isn't 9 to the 2x? How come it's just 9 to the x?
So when you do u square, you would do 3 x to the second power, right?
Mm-hmm.
And the rules of the exponents, you multiply these two. And then you can rewrite this as 3 squared to the x, right? So that's 9 to the x,
Okay.
right? So you only squared it once, so to speak, right? Right there, you were squaring both the 3 and also the multiplying the exponent by 2. So you do one of the two. You either write it like this, 3 to the 2x, or 9 to the x.
Okay. Thank you.
You're welcome. Any other question? Okay, we'll continue tomorrow then. Stay safe, guys. See you tomorrow.